Okay, let's start today's session. As usual, guys, please write your name on the chat so that I know you were here, and we'll continue where we left off. So last time we talked about this new system of polar coordinates, right? With polar coordinates, we can describe curves that go around. That's what these are really great for describing curves that have radial symmetry, right? Things that go around in an intrinsic, in a way different than from regular rectangular coordinates. And what we're going to be working on today is now, so last class we talked about how to go from rectangular to polar, and we also concentrated on how to draw the graphs of polar equations. If we were given something like r equals 1 plus cosine theta, how do we draw that? And it turned out to be this nice, beautiful cardioid. And today we'll talk about calculus related to those graphs. So we'll start with the slope of the tangent line. So that's the one we'll do today, and we'll move on to a few others after that as well. So let's go to the paper and start with the slope of the tangent line, right? All right. So what is this problem? Well, the classical problem of the slope of a tangent line is the following. So say we have one of those graphs that we were studying yesterday, like this our cardioid, right? This 1 plus cosine theta. And we ask ourselves at some point over here, what is the slope of the tangent line, right? So find the slope at a given theta on the graph of r equals f of theta. All right, so that's the general question. And how do we do it? Now we know on regular rectangular coordinates that the slope is the derivative evaluated at a given point. So it would be sweet if the same formula worked here. Sadly, that's not the case. So the answer here is not going to be the derivative of this function evaluated at theta, right? So let me put it over here as a warning. So the answer is not f prime of theta, right? So don't expect it to be as simple as that. Okay, but it's actually not that hard once we think about it, right? And the way to think about it is to realize that we already answered this problem for parametric equations. So when we did it for parametric equations, so let me just write it here. Recall that for parametric equations, x equals f of t, y equals f of t. When we have parametric equations like this, then we figured out what is the slope. So the slope was dy dx at some t0. And it was easy. All we need to do was dy dt divided by dx dt. That's the formula we discovered, and evaluate t0. So in other words, it was just do the derivative of the top function and do the derivative of the bottom function and plug t0, right? So that's what we did for parametric equations a couple of classes back. So the way we now should figure it out for polar equations is to use these and figure out how can we relate a polar graph to a parametric graph? And it's actually not that difficult because, so here's the thing, note that here we know what x and y are in terms of the polar equations, right? We discovered that yesterday. X was r cosine and y was r sine. If you had forgotten about this, let me quickly remind you. It's not that difficult. So if you have your axis of regular xy coordinates here, where this is x and this is y, and this is theta and this is r, then if you use the sine of this angle, is the opposite over the hypotenuse. So sine of theta is y divided by r, and cosine of theta is x divided by r. So if you simply solve for x and y, you get this one over here. Okay, so that's what we have. But here in our particular setting, we know that r is a function of theta. So r is f of theta. And that's fantastic because now, well, what we can do is plug it in, and then we get this r, which is f of theta, times cosine theta, and y is f of theta times sine theta. Look, these are like parametric equations, right? These are parametric equations, but the parameter is not called t, it's called theta. But so what? I mean, it's just a different name. So these are parametric equations on theta. And that's fantastic because now we can figure out what is the slope, right? We just need to do what we did before. So the slope is simply going to be dy dx at a specific theta that you want. And to do that, all I need to do is do the derivative of y with respect to theta divided by the derivative of x with respect to theta and plug theta 0. And okay, so how do we do the derivative of y with respect to theta? Well, product rule, right? There are two functions here, so we follow the product rule. So the derivative of the first one, that's f prime of theta, times sine plus f times the derivative of sine, which is cosine, divided by the derivative at x. So it's the derivative of the first one, that's f prime of theta, times the second one, plus the first times the derivative of cosine, which is negative sine. So that negative sign makes this a minus. And we plug theta 0, so I'm just gonna plug theta 0 here. And that's it. That's, if you want it, the formula for what is the slope of the tangent line at a specific point. So as you can tell, it's not the same, right? It's not the same as simply doing f prime, right? It's f prime times sine plus f cosine, etc. But I recommend that you remember where it comes from. That way you don't need to remember this formula that is complicated. You can simply remember that you need to do this, which is, well, I mean, this is easy to remember because this is just r cosine theta and r sine theta. Plug what r stands for, and then take the derivatives with respect to theta. The derivative of the y on top, the derivative of the x on the bottom. And that's how we figured it out, all right? So this is it. This is the slope formula. The slope at a specific angle. And there's a special case worth noting. So what if you have a point that goes through the origin? So if f of theta 0 is 0, So if the radius is 0, right, that means if you go through the origin, i.e. we are at the origin, if that happens, then this is 0 and this is 0. These two cancel, right? And if these two cancel, then you can also then cancel the f prime theta 0 and the f prime theta 0. These two cancel as well. And look what is left. The only thing that remains is sine of theta 0 divided by cosine theta 0. Which you can better write it as tangent of theta 0. So that's a special case. Yes, it's just worth noting that you get something cute and short if you happen to go through the origin. All right? So let me show you the statement from the book before we move on to some examples. So here's the statement from the book, slope of the tangent line. It says if we have if f is a differentiable function of theta, then the slope at the slope of the tangent line at the point with polar coordinates f of theta theta is given by this one over here, right? Which is just the one. Oh, I can't highlight it that nice here, but this one over here, the formula that you see in the center, is the one we just deduced, and it even says that when you go through the origin, then it becomes tangent of theta 0. All right. So let's work on a couple of examples, starting from the first one that you see right there. So example 1, slopes on a circle. It says find the slopes of the lines tangent to the circle r equals 10. So in here, r equals f of theta equals 10. Okay. And I'm just gonna write the formula that we have on the screen right now so that we can use it as reference, the one we just figured out. So this is the one we need to do. This is our graph. It's just a circle, right? R equals 10. So we can draw it here. So the radius is 10 and it's just a nice round circle. And this is the formula we deduced. So all we need to do is figure out what is the derivative, right? So in this case, f of theta is 10. So what is f prime? What is the derivative?
0.
Yeah, 0, right? It's just a constant. Thank you. The derivative is 0. So then dy dx is simply, let's see, these terms cancel because the derivatives are 0, and this is 10. So it will be 10 cosine theta 0 divided by negative 10 sine theta 0, right? And the 10s go away, and this is cosine over sine. So this is just negative cotangent theta 0. And that's it, right? So it doesn't matter what graph you have. You can test a few points. So for example, when theta is pi over 2, theta equals pi over 2, what do you get? You get negative cotangent of pi over 2, and that's 0, right? So this is telling me that when it's 90 degrees, the slope should be 0. And we know that, right? It's this horizontal line right here. Let's do another one. How about pi over 4, 45 degrees? It would be this at 45 degrees would be this point right here. So it would be this line. It looks like -1 to me. Let's just check. So it would be dy dx equals negative cotangent of pi over 4. And that's negative cosine of pi over 4, which is radical 2 over 2 divided by sine pi over 4. So it is negative 1 indeed, right? Just like we said it should, all right? Okay, let me go back to the book. There's more pictures there. Where's the book? Right here. So right here on the side, you can see a few more. Right, so we did at pi over 4 is negative 1, at pi over 2 is 0. Here you have a few 4. So at pi it's going to be undefined, so cotangent of pi is not defined. And that makes sense because the line is vertical, right? The same happens at 0. So at both 0 and pi, the slopes are undefined, and that makes sense because we have vertical lines. Okay, good. Let's take a look at example 2 now. A bit more interesting. So now we'll look at this cardioid shape. It says find the points on the interval negative pi to pi at which the cardioid f of theta equals 1 minus cosine theta has a vertical or horizontal tangent line. So we need to find vertical and horizontal tangent lines, and it's the cardioid is 1 minus cosine theta. So our R is 1 minus cosine theta. All right, let's do it. So this is our new function that we need to work on. So it's a cardioid. Maybe we should let's do a little bit of extra work. Let's actually try to sketch the graph of this, right? Let's start with that. So here's it says from negative pi to pi. That's the angles we want to work at. So like we said before, we start by looking at the regular rectangular graph from negative pi to pi. So right here, negative pi to pi, and this is going to be the graph of 1 minus cosine. Okay, so how does that one look? Well, cosine of 0 is 0, so this is 1 minus 0, so it starts right here, and it's like the graph of negative cosine, but 1 unit down, right? See, am I doing this right? So let's see. Cosine of 0 is 1. So it starts right here. Yes, and then is like the graph of cosine, negative cosine. You move 1 unit up. All right, so it's like this, and it goes. Cosine of pi is 1. Okay, let's maybe plot a few more points. All right, so at pi over 2, what's going to happen at pi over 2? We have cosine of pi over 2, cosine of 90 degrees, and cosine of 90 degrees is 0. So at pi over 2 is 1, so it's all the way over here. And then at pi, cosine of pi is negative 1. So this is negative 1, and negative 1 is going to be 2. Okay, so I need a better scale here. So let's say that this is 1 and this is 2. Should have put this axis lower. So cosine of pi is, at pi is 2, and at pi over 2 is 1. And over here is here and here. So I think it is this graph. And then it repeats itself. All right? So that's the graph of R equals 1 minus cosine theta, the regular rectangular graph. And right here in the bottom, now we're going to draw the polar graph, right? Let's see if we can do it. So we start at 0. And at zero, at angle zero, the graph is, the radius is 0, right? Then from 0 to pi over 2, it grows all the way to 1. So from 0 to pi over 2, it grows all the way to 1. So it grows all the way to 1, like this, right? Growing, growing, growing till it reaches 1. We're right here. Then from pi over 2 to pi, grows even more all the way to 2. So 2 is over here, 2 units, right? So from pi over 2 to pi, so as we sweep from 90 degrees to 180 degrees, it's going to grow even more all the way to 2. So it's going to go like this. Okay, and that's it. We did this part. And now the other part is the same, but going backwards, right? So from 0 to negative pi over 2, so if we sweep backwards from 0 to negative pi over 2, if we sweep this way, the angle is going to be, the radius is gonna increase from 0 to 1. So right here is 1, and it goes again like this. And then from negative pi over 2 to negative pi, it grows even more all the way to 2. So it's going to go all the way over here. And it's this nice cardio, 1 minus cosine theta. Okay, now this was not part of the problem, but I wanted to give you a little bit of practice about doing this part, how to sketch a graph in case you need to, you know, figure it out how it looks like, right? So now to figure out the slopes. So we need to find out horizontal and vertical tangent lines. In other words, where the slope is 0 or where the slope is undefined because we're dividing a number by 0. Okay, so here's a formula. So dy dx is f prime times sine plus f times cosine divided by f prime times cosine minus f times sine. Notice how it alternates. So this is sine cosine, and then this is cosine sine, and then the bottom one you have the minus sign. All right, that's a way to remember it in case you want to memorize it. Okay, so in this case, f of theta is 1 minus cosine theta. So what is f prime? The derivative of 1, nothing. The derivative of negative cosine, that would be sine. So let's put it in here. So f prime is sine, so now it's sine squared plus f is 1 minus cosine, and then cosine. I'm writing theta instead of theta 0 because it's simple. F prime is sine, and over here is 1 minus cosine times sine. All right, let's simplify it. This will be sine squared plus cosine minus cosine squared divided by sine times cosine minus sine plus sine times cosine. Right? So what we really have is how do I write it? Let's write it as cosine theta plus sine squared theta minus cosine squared theta divided by, and what do we have in the bottom? In the bottom is 2 sine theta cosine theta minus sine theta. All right, so that's the derivative, right? So we're halfway there. We just figured out what the derivative is. Next step is we need now to find out when the numerator is 0 and when the denominator is 0. All right, so first, horizontal tangent lines. So horizontal tangent lines, when numerator is 0 and the denominator is not? Because if both of them are 0, then we don't know. It's like an indeterminate, right? There's a way to do it. We can use L'Hopital's rule to figure out which one wins, but let's worry about that when the case comes, okay? So when the top is 0, so that would mean cosine theta plus sine squared theta minus cosine squared theta is 0. All right? Now, we need to solve for theta here, and this is difficult because we have sine square and cosine square. So the first hint here is to get rid of sine square, because it's better if we only have one trigonometric formula, and in this case, the better way is to give everything instead of cosine. So let's change this sine square. So that will be 1 minus cosine square. And now this becomes -2 cosine squared theta plus cosine theta plus 1 equals 0. Or, let me continue over here. I'm going to put it the first one positive because it looks better. Like that. Okay. So next, what we want to do here is solve for cosine theta. Think of this as a quadratic equation in cosine theta. Okay? By the way, I'm not doing calculus here anymore. This is just algebra, right? We did the calculus part already when we figured out this formula. This part over here is simply algebra, right? And I know it looks complicated, but it's just simply, you know, solving an equation. That's what we're doing right here. So here, maybe we can try to factor it. Let's see if we can do it. It should be like this. And then look for numbers here. It should be like 1 and -1. So I'm thinking -1 here and 1 here.
Professor? Should it be +1, not -1?
Should be +1 here. Yes, thank you. Which then changes this, right? Let's see. Now both of them should be maybe 1. Now I don't know if it's gonna work. Let's see.
Oh wait, did you distribute a -1 for the whole thing?
Yes, I divided by -1. That's what I did.
Oh, okay. Never mind then.
So, oh no, it was minus, right?
Yeah.
Yeah.
Okay, you're right. Sorry.
No problem. So it was minus. Yeah, so I just, I don't like it when the leading coefficient is negative, so I multiply by -1 everything, and that's how we got this one. And now we're looking for two numbers that the multiplied give -1, and such that I get the middle term, and I think it's -1 here and +1 here. That works. Let's check. This would be -1, yes. And then 2 cosine, -2 plus 1, it will be -1, good. And this works too. Great. That works. So then I get two equations here. One of them is cosine theta equals 1. And this one is cosine theta equals -1/2. Right? Now, what angle gives you a cosine of 1? Between -pi and pi, that's our domain. And this will be cosine that gives you 1 is 0, right? So only one solution. And over here, angle that gives you -1/2. So what cosine gives an angle of -1/2 as cosine? So -1/2 means, let's see, we wanted it to be, here's our unit circle, -1/2. So it's one of these two angles, right? So 2 pi thirds or -2 pi thirds. All right. Next, the vertical tangent lines. So this time is when denominator is 0 and numerator is not. Okay, so the denominator was this one over here. So let's write it. So we want 2 sine theta cosine theta minus sine theta to be 0. Okay, and this one is actually a little bit easier because we can factor the sine theta. So we get two solutions. Either sine theta is 0 or cosine theta is 1/2. In this one, the angle with which sine is 0 is just 0. And in here, if the cosine is 1/2, that means the angle is pi/3 or negative pi/3. All right, so good. So we almost have the problem. The only issue is 0. I hope you see it, right? So we have these numbers over here, which are candidates for horizontal tangent line. So 0, 2 pi/3, and negative 10 pi/3. And these numbers over here, that are candidates for vertical tangent lines where the slope is undefined. And the only problem is, I mean, these work. So these are already good because these appear in this list but don't appear on this one. So these ones for sure give you 0. And these also work. These for sure are undefined because you get 0 in the denominator but not 0 in the numerator. So the only issue is 0. 0, we're not sure what's going on with 0. So to figure out what's going on with 0, we need to try to do L'Hopital's rule, right? So try to see what happens when we get close to 0. So we need to figure out what is the limit. So to find the truth about 0, we need to use L'Hopital's rule. All right, so specifically, we need to do the limit when theta approaches 0 of cosine theta plus sine squared theta minus cosine squared theta divided by 2 sine theta cosine theta minus sine theta. And right now, when we plug 0, we get 0/0, right? We verified that already because the 0 happens in both of my lists. So right now it's 0/0. So we can apply L'Hopital's rule. So it will be a little bit complicated because these derivatives are not super easy, right? But let's do it. So it will be the derivative of cosine plus the derivative of sine squared as 2 sine theta times the derivative of sine, which is cosine theta, minus the derivative of cosine squared, which is 2 cosine theta, times the derivative of cosine, which is negative sine. All right, in the bottom is the derivative of 2 sine theta cosine theta, so we use the product rule. So it will be 2 times the derivative of sine is cosine, so that's cosine squared, plus sine times the derivative of cosine, which is negative sine, so it's cosine squared minus sine squared, minus the derivative of sine, which is cosine. All right, now let's simplify that and see if we can figure it out. Hopefully cancel something out. So this is plus, so it's 4 times sine theta cosine theta minus sine theta in the top. And in the bottom, we have 2 times cosine squared theta minus sine squared theta minus cosine theta, right? And we want to do it when theta approaches 0. So let's plug 0 and see what happens. So what happens when we plug 0? Sine of 0 is 0 and sine of 0 is 0. So on the top we get 0. But on the bottom we get cosine of 0, which is 1. And then cosine of 0, which is 1. So this is 0 over 2 minus 1. So it is 0. All right? So 0, 1. Right? So it was 0 over 0. And when we did L'Hopital's, we still got 0. So that means the 0 on the top was a stronger one. So because we got 0, that means at theta equals 0, we have a horizontal tangent line. All right. Now let's check with our picture. Let's check that this works with our picture. So where it was my picture? Did I leave it? Here. So here's the picture that we created before, right? So according to our results, it says that we have horizontal tangent lines at 0, 2 pi over 3, and negative 2 pi over 3. So at 120 degrees, that will be right here, 2 pi over 3. And that's true. That's a horizontal tangent line. And also at negative 2 pi over 3. Okay, my picture is not perfect, but the tangent line should be right here. And at 0, right here, that's another tangent, horizontal tangent line. And then vertical tangent lines at pi over 3 and at negative pi over 3. So at pi over 3 right here, that's a vertical tangent line, and it's the same as negative pi over 3 right here, right? And we have another one at, we should have one at negative pi and at pi. Let's see, where is it? Did we not get that one? Oh, I forgot about that one, right? That's a good thing about looking at the picture. You see right over here, when we said sine of theta is 0, I only put the one solution. I only put the solution theta equals 0, but I'm missing others, right? I'm missing pi and negative pi. I had missed those, right? That's a good thing that I went back and looked at the picture. And those work because they don't appear on this other list, right? They're not in this other list. Pi and negative pi are not in here, so they work, and that's correct. At pi and negative pi, we are right here. It's the same point, because when theta equals pi, we're here. When theta equals negative pi, we're here. So it's the same point, and we have this vertical tangent line right there. Okay. Okay. Are there any questions? Let me put the picture from the book while some of you think about questions in case you have some. So there's a better picture in the book about the problem we just did. Just want to show it right here. Yeah. So that's precisely the one we found. So horizontal tangent line at 0, and also at 2 pi over 3 and at negative 2 pi over 3. Vertical tangent lines at pi over 3, negative pi over 3, and at pi and negative pi, where the slope is undefined. Okay? Good. Let's move on and talk about the next important concept, and that's the concept of area, right? So the next thing we would like to do is see if we can figure out what is the area, say, inside this cardioid. What is the area inside this region? how can we calculate things like that? Areas inside polar equations, right? Areas determined by polar equations. So since I have the screen right now on the book, let me do it right here. Look, so we need the next page, I believe. So page 781, and it has the appropriate diagram. So the idea will be the thing we usually do. So we're gonna slice and dice, right? And the main important notion that we need is this one: how we can get the radius of a pie of a slice of pizza, right? What is the area of a slice of pizza, like you see right there on the screen? If you have a circle of radius r and you have an angle delta theta, what is the area of that sector? And it's really easy. It's just the only thing you need to do is to divide what proportion you are cutting, right? So if your angle is 2 pi, if you have everything, the area is pi r squared. We know it. So all we need to do is divide the angle that we have, which is what we have over here, delta theta, by 2 pi. And that's going to be the fraction of the area, correct? So if you have a half of the angle, half of the total angle, then you get half the pizza. If you have 1/4 of the total angle, you get 1/4 of the pizza. So if you get delta theta of the angle, the proportion of the pizza you have is delta theta divided by 2 pi. And when you do delta theta divided by 2 pi times pi r squared, like I'm highlighting right now, you get this formula: 1/2 r squared times delta theta. Okay, remember that, because that's essentially the only area formula we're gonna need. That the area of a circle of radius r and angle delta theta is 1/2 r squared times delta theta. That's all we need. Okay, and then what else do we need to figure out the formula? Well, the only other thing we need is to slice, right? So here's what we're going to do. We're going to, so here's our goal. Our goal is we want to figure out the area. Let me show you this picture. We need to figure out this area, the shaded in blue area. And what is that area? Well, we have this curve. We have this curve r equals f of theta. And we want to find out what is the area from theta equals a to theta equals b. So from one to the other, right? I should do the other way around, like this. I forget that the image is my mirror image. So from here to here, right? That's what we're doing. And the way we're gonna do it is we're gonna slice this angle into little pieces. So just like the red lines that you see right there, we're gonna slice it into different angles from theta equals a to theta equals b. Slice, 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 slice. All right? Now I'm gonna move to the right to tell you what the approximation is going to be. For our approximation, once we have those little thetas, what we're going to do is we're gonna approximate each one of these pieces with a sector of a circle, with a little slice of pizza. So slice of pizza, another slice of pizza, and so on. Those are these little arcs that you see on blue. That's our approximation. And it's gonna be an approximation. You can tell that this piece over here, where I have the cursor, has this extra piece that we shouldn't have. And it's missing this part over here. So it's gonna be an approximation, but it's gonna be a better and better approximation the more and more pieces we take. All right? So, so what is going to be the approximation? What is the sum of all of these areas? And it's written right here. So the approximation, the area approximated by these slices will be when I add up all of the slices. And adding up all of the slices means doing 1/2 of f of the angle that we chose to figure out where to cut the slice times the little angle. And the little angle is delta k, right? And then what happens when we let n go to infinity? Well, this becomes a so-called Riemann sum, right? And that will be on the next page, right? Or I can write it on the screen actually. So let me put this one here, and I write it I'll do it handwriting. So the area we have is approximated by adding up all of these pieces. And what we want to do now is take the limit. Take the limit when we move this to infinity, right? So that's the area we have, right? And when n goes to infinity, when we take the limit when n goes to infinity, this Riemann sum becomes an integral, right? The integral from alpha to beta, right? Where we started to where we ended. Let me do our picture over here of our situation. So we were doing from alpha to beta, and we had some curve here. We want to get this area. So this is going to be 1/2 f of theta squared d theta. And simple formula, right? I mean, remember, you don't need to deduce where the formula comes from every time. You only need to know the formula. So here is the formula that we want. It's a simple one. We can take the 1/2 out. So it's just the integral from alpha to beta of the square of the function. Super, super easy, right? Super straightforward, easy formula. The beginning angle, the ending angle, the function square. It's as easy as that. All right, let's put it in practice. Oh, and actually, so the same as we have done in the past, if you have the area between two graphs, let me show that in the book. So if we have the area between two graphs, then all we need to do is do the integral from one minus the other, right? Let me show it to you as long as the page loads. So the picture is right here. So if we want to get the area of this region R, the light blue region R, and that's given between one angle and another, but also in between two curves, right, from F and G. The only thing you need to do is kind of like get the area of the big one and subtract the area of the little one, right? And you can accomplish that by doing what is written right here. So doing the area, the integral from alpha to beta of 1/2 the f squared minus the g squared. That's how you can get the area in between the two curves. Okay, is that clear? Let's do an example. Sample 3. It says find the area of a 4-leaf rose. In fact, it's right here. So let me put it. So this is the summary of what we just said, right? If it's in between two curves, we do it that way. And that's the example. We need to find the area of the 4-leaf rose. If you remember, we did the graph of that one last time, or one very similar to it. Mm-hmm. So it looks like this. And just, I sort of draw it the way it's supposed to go along. So that's this graph, 2 cosine 2 theta. Now, using the symmetry, maybe we don't need to do a complicated integral. We can simply do this is symmetric. So each one of those 4 petals is the same. So we can try to simply do the area of one of the petals, or even 1/2 of the petals, right? Maybe we should try to only do the area of this part over here. Right? My picture is not great. This should be the same as the bottom one, right? Like this is slightly better. So these 2 should be the same as these 2 should be the same, and these 2 should be the same. All right, so let's try to do this, to do the area of this orange shaded part. So we need to figure out the angles, right? Now, what are the angles that correspond to this? So in other words, try to figure out the alpha and the beta. From where to where are gonna be doing our integral? So the area function is, the area formula is very easy. Let me write it here. The complicated part is to figure out the alpha and the beta, right? So right now, this one is easy. This one is when theta is 0, right? When theta is 0 at angle 0, you start at cosine of 0, which is 1 times 2. So that's why the graph starts here at 2 units away when the angle is 0. So now we need to figure out what is this one over here. When is it that it comes to 0, right? So what is the first angle after 0 where cosine becomes 0? So after theta equals 0, the next value for which cosine 2 theta is equal 0 is, well, cosine is 0 when the angle is pi over 2, right? So it's got to be when 2 theta is pi over 2, i.e. when theta is pi over 4. So right here at pi over 4 is when we get to 0. So we want to integrate from 0 to pi over 4. Is that clear? From 0 to pi over 4. And we only have one function here, right? We want the area under the curve on this, right, on this ray, right, on this cone, under the curve, on this side, right? On this side over here. So here's the area. So the area that we want, well, that's actually 1/8 of the area, right? 1, 2, 3, 4, 5, 6, 7, 8. So 1/8 of the area that we want to calculate, is given by this formula: 1/2 the integral from 0 to pi over 4 of the function. What's the function? This is the function, right? 2 cosine 2 theta, quantity square, d theta. All right, so that's it. We did the hard part, the setting up the integral. The rest should be straightforward, right? It's just calculating the integral. And it's not a terribly difficult integral, but let's do it anyway. So let's, I'm gonna multiply by 8 to get really what I want. So 8 multiplies this, so it's 8 over 2 is 4. And I'm gonna get another 4 coming out of this. 2 squared is 4. And then it's cosine square of 2 theta. Right? Now, do you remember how we do this trigonometric integral? What is the technique here? If we have cosine square, 1 minus sine square, that still gives the problem of doing sine square, right? But so not quite that, Michael. Instead, we want to use the half angle formulas. Remember those? So those are when we have cosine square of x, that's 1 minus cosine 2x divided by 2, and sine square x is 1 plus cosine 2x divided by 2. Let me, I'm a little, I have the right, let me see. I think this is plus, actually. And yeah, they're correct. So it's the positive one, right? So this will become then 16 times. And instead of cosine square of 2 theta, we're going to write 1 plus cosine 4x, 4 theta, over 2 e theta. And 16 and the 2, that's now an 8. 1 plus cosine 4 theta. And now we can, we should be able to integrate. The integral of 1 is just theta. And the integral of cosine 4 theta is sine 4 theta over 4. And we're doing this from 0 to pi over 4. So we plug pi over 4, and that's pi over 4 plus sine pi divided by 4, minus, we plug 0, and that's 0 plus sine 0 divided by 4. So here 0, 0, and sine of pi are all zeros. So the only thing that survives here is the 8 and the 4, the 8 and the pi fourths, I mean. So that's actually 2 pi. So the answer is 2 pi. Okay, let's do another example. For this, I think we also need the picture to take a look at the. I mean, all of these problems, by the way, are harder if you don't know the picture, right? It's always easier if you're provided the picture of what you want to do. And this is one of these situations as well. So I think we'll only start this problem and we'll finish it up next time, but I want to get it started. So here is the problem. It's example 4. It's going to be right here in next page. So as you can tell, we have this cardioid. The cardioid R equals 1 plus cosine theta. And we have this circle. And here are the questions. Question 1. Find the area of the region inside the circle and inside the cardioid. So find the part that is both inside both of them. And part B, find the area of the region inside the circle but outside the cardioid. So in one of them, we want to find the area that is right here inside the circle but outside the cardioid, and that's part B. And in part B, we want to find out the area of the light blue and the red together, right? The light blue and the red together. And I don't know if you realize the red is super easy, right? The red is just half a circle. So that part is very straightforward. So to do the inside to both, maybe we just need to do this little part, the light blue, the light blue. Or here's another way. We could get the light blue and the red together. We can get out the circle and figure out the part that's outside and then subtract that from the total area of the circle, right? That's a way of doing both at the same time. So let's try that. So let's start by trying to set up what is the area inside the circle but outside the cardioid. We'll at least try to start setting up the integral. So here's my picture. And remember, initially, what we want to do is try to find out this one. So inside the circle and outside the cardioid. So that way so that means we want to integrate. Maybe we only do half of it. Again, we can use the symmetry. We want to integrate from here to here, right? So from this part to that part, right? And this part is when the angle is pi over 2. So this is theta equals pi over 2. And this is when theta equals pi, right? And then we have the outer function is the circle, right? And the inner function is the cardioid. So the area of half the region, so 1/2 of the area that we want, is the integral from pi over 2 to pi, so from here to here, of the outer the outer part, the outer function is 1. So I'll write the formula. So the formula is the outer part, the outer function minus the inner function, d theta. And in here, the outer function is 1, and the inner function is 1 plus cosine theta. Those are the ones that you need to plug in here. So 1/2 of the area that we want is the integral from pi over 2 to pi of 1 squared minus 1 plus cosine theta squared d theta. All right? We're done. We set up the integral. So all we need to do now is complete that integral to figure it out. And we'll do that by the beginning of next class. And that is almost all that we need to do. We have another little topic to finish this section, which is the arc length, the length of a curve, right? The length of a polar curve. We haven't talked about that one either. But then after that, we're set. So I'm hoping to finish the material at, you know, the middle of tomorrow's class, so that we can have at least half a class for review and then all of Thursday's class for review as well. Okay. Now, I have already set up, yeah, so question is, when will you get your scores for exam 2? As soon as possible. So as I told you before, I mean, this new way of teaching has taken a lot of time to set up, and I'm behind, so I haven't finished grading your tests. So I'm working on them, but as soon as I have them, I will post them on our Canvas page. Am I gonna teach Math 250 next semester? No, I'm gonna go back to teach 150A and 450A, Advanced Calculus, if you're interested in doing that one. Other questions? So start going over the material. Yeah, so Daniel is asking, why do I have 1/2 the area equals 1/2 the integral? And the answer to that is because I am only calculating half of the region that I want. Let me go back to my picture. So the question that was asked of us is to do all of these, all of the orange part, but I'm only doing this part. So that's why I put 1/2 the area. All right. Hope that answers your question, Daniel. Okay. So bring your questions, bring any problems that you're having difficulty with, have them prepared for tomorrow's class and also for Thursday. I have already set up as an assignment on Canvas, but it's not open yet. So the way it's gonna work out is the exam will open up at 1 p.m. on Thursday, and you're gonna have till 1 p.m. on Friday to upload it. All right. So it's 24 hours, but that takes into account the time in which you need to upload it. So take that into account. Please don't leave it till the end, because I won't grant extensions. Okay. So you need to have you need to upload your solution to the exam in that 24-hour period. My suggestion is that you finish the exam by Friday morning, and then in case you have any difficulties, technical difficulties, you can still contact me and we can figure them out. Gisela is asking, will it be the same format as previous exams? The answer is yes. So we'll have a few multiple choice questions at the beginning, and then it will be as the same as our regular exams. Now you're supposed to do the work on your own. So at the first page, there's going to be a page that you need to sign, where you a statement that says that your work is your own, that you didn't get help from any outside person, and that you're not using any electronic devices, either calculators or you know, Google or computers or anything to figure out your answers. All right. So we're going to go on the honor system for that, but you need to sign up that statement. Okay. All right. Any other questions?
Yeah, Professor?
Yes.
So, well, I have a few questions. For the first one is, should we print it out or could we write the questions down on a piece of paper?
I would prefer if you use the space that we have for the test. That way it will be easier for me to grade. But you could actually write them down on your own. That would be fine as well. And also you can upload one page at a time, or what I'm gonna recommend is that you create one file, a PDF file with your entire exam, because that will make it easier for me to grade. If you make it one page at a time, then every time that I want to see a new page, I need to click and then wait for it to load so that I can look at it on the screen. And then that's gonna, you know, make it so that it takes even longer for me to grade your exam. So preferably, and I'm gonna put that in the instructions, preferably try to come up with one PDF file for your entire exam. If you don't know how to make PDFs from pictures from your phone, there's tons of applications. You can Google it and you can find out different apps that can make that for you.
Okay, and also, how did you know the circle was the bigger function to subtract?
Because it's the one that is farther away from the origin, right? So the one that is farther away, that's the outer function. The one that is closer is the inner function. So let me go back to the page and I'll show you a little array that could probably show you what I mean by this. So if I draw a ray right here at this angle, right, this ray, the farther away point is the circle, and because it's farther away from the origin. The one that is closer, that's the inner function. So that's the outer and that's the inner. Does that make sense?
Yeah, thank you.
If we write down the questions on your own paper, you still should print out the one that, or you can write in your own handwriting the statement and then sign after that. Alexandro asked, if we write down the questions on our own paper, how do we sign it, the academic honesty part? Well, you either transcribe it or you take the first, it's going to be on the first page of the exam where you write your name. You can then take a picture for that one and append it or prepend it to your exam. Okay, anything else? Very good. So I'll see you guys tomorrow. A reminder, I'm still uploading all the videos for a session. So if there's anything that you want to review, or if you didn't get to the class on time, you can always go back and go over the video. All right, I'll see you guys tomorrow.